Tim Besard from Julia Hub. I guess many of you already know him, and he will present some advances of the Julia GPU stack, particularly about CUDA.jl and oneAPI.jl. Thank you.
Thank you. Thanks for the introduction, and welcome to my talk. As mentioned, I'll give a brief overview of what we have been doing in CUDA.jl and oneAPI.jl since the previous version of this talk at JuliaCon 2023. I'll start out with CUDA.jl. And as you can see, we've had plenty of contributors this year. So thank you, everybody who has contributed to the package. There's been plenty of versions, and I'll give a brief overview of the highlights, especially to an HPC audience or a performance-focused audience. And personally, I think that the profiler that we added, the integrated profiler, is one of the most interesting additions to the package, because it allows you to gain quick insights on the performance of your application. It be an entire GPU application or just a single GPU kernel. You can just put CUDA.add_profile in front, and you'll get a summary of the GPU activity on the device, as well as the activity on the CPU that's GPU related. So here, for example, I'm allocating some data on the CPU, uploading it to the GPU, and then doing a simple broadcast addition by one. And you can clearly see on the bottom end where we have the device-side activity that there's both a copy and a kernel being executed. It's a summary, so it's ordered by cost. So at the top you have also bolded and in red the most expensive operation that happened. And on the CPU side, we see which API calls were required for that, as well as the statistical distribution of the execution times when there was more than one call to that function. This is some great overview, a great summary of the performance. And if you're optimizing an application, what you will want to try and do is to optimize the ratio of the device being active in relation to the entire trace. So with this very simple operation, we see that the GPU was only active 2% of the time, and the CPU actually was busy 50% of the time doing work to submit these operations. But that's kind of expected with such a simple operation. Generally, with a more complicated operation, you ideally have the device active all the time and the CPU not spending too much time to queue up that work. So this is a summary view. We also have a trace view where you get a chronological trace of the operations that happened, again, both on the host side and on the device side. Because all of the operations are now separated apart, they're not summarized anymore, we can provide additional details on each operation. So again, on the device side activity, we can, for example, show what the launch configuration of the kernel was, how many registers were used. In the case of the copy, we can show how much memory was copied, how quickly that copy went, the throughput of it, and so on and so forth. Again, this can be very useful for optimization, but this can also be useful to just get some insights on how an operation or how an application works behind the scenes. And I'll use it to give some insights on one of the other noteworthy improvements to CUDA.jl over the last year. Namely that calling the synchronize function, which is sometimes something that you often do or happens often behind the scenes, making the CPU wait for the GPU to finish computing. That happens implicitly when you copy memory from the GPU to the CPU, because we need to first wait for those values to materialize. But it also happens when, for example, you call the MapReduce function and you reduce an array to a scalar. Now we have to first wait for the GPU to finish computing and for the scalar value to be available. So in order to do that, we call the synchronize function. We used to call the synchronize function on the main thread of computation. The result of that was that essentially your thread of computation was blocked until the GPU finishes. With the new version of CUDA.jl, we're now doing these synchronization operations on a separate thread. So you can see in the column that the call to QStream synchronize was actually performed on a new worker thread. And this allows the main thread of execution to remain available to perform other work concurrently with that synchronization happening. And this is, of course, great for concurrency. It allows you to overlap synchronization of GPU code with other Julia code. Other Julia code that could, for example, be submitting other work to the GPU or just doing CPU computation. That's all possible. It does also improve latency in some cases, because the old implementation was actually dependent on, it could get blocked with operations happening in libuv, which was always pinned to a single thread. Bit of a detail, but I know that some HPC people have run into that, where the latency of some operations spiked because of contention on the main worker thread. That said, launching code on the thread, of course, involves some overhead as well. So initially, we will be spinning a couple of times to see if the API call is brief enough that we don't need to perform the synchronization on a separate thread. For example, here I'm doing a very short API call, and as a result, we can just do the synchronization on the main thread of execution instead of sending that work over to a separate thread, which again also involves some overhead. Hopefully that design should make it possible for everybody to use this without inducing additional latency in the application. Nonetheless, I've heard for some people that applications which are extremely latency sensitive even cannot risk running into this. And for them, it's always possible to pass the blocking equals true argument to the synchronization functions in CUDA.jl, which will make it immediately call into the blocking function just like before. And it's also possible to set this with a preference. So if in your local preferences.toml you specify non-blocking synchronization equals false, then we'll also always be using the old implementation that guarantees better latency. Again, in general, I don't recommend this. It's also possible to improve the heuristic on our side when we spin, when we use the thread. So if you have issues, get in touch with us. Maybe we can improve the situation for everybody else. We also did a whole bunch of work on unified memory. So unified memory is a form of GPU memory that's accessible from both the CPU and the GPU. It's not the type of memory that we use by default. By default, we normally use device memory, and device memory is only accessible from the device. And you may have run into the limitation of device memory when porting a CPU application to the GPU and then accidentally triggering some fallback functionality from the CPU side, which, for example, still contained a for loop. The for loop would then be iterating over individual values of the device memory. And when the system detected that you were fetching an individual scalar from a QArray, we actually throw an error. And that is because, again, device memory is only accessible from the GPU, and if you access it from the CPU, you pay a huge performance penalty. Now, unified memory can help with that because, as I mentioned, unified memory can be accessed from both the CPU and the GPU, meaning that these kinds of scalar accesses are allowed. And this makes it possible to incrementally port functionality or applications from the CPU to the GPU without risking or being afraid that if you trigger fallback functionality, it'll be slow. And this is made possible by optimizations in CUDA.jl 5.4, where here I show the performance of doing the access of device memory. You can temporarily allow it by doing CUDA.add_scalar. And as you can see, accessing a single scalar from device memory takes 10 microseconds. Doing the same with unified memory only takes 4 nanoseconds. So that's orders of magnitude faster. And just as a comparison, fetching a single value from a Julia CPU array takes about 2 nanoseconds. So it's in the same ballpark. And of course, benchmarks at these scales aren't really to be trusted, but nonetheless, it shows that the performance improvement of accessing unified memory in a scalar fashion is much, much, much improved. And the main goal of this is to make it much more easier to port existing CPU code to the GPU and without having any performance issues introduced by doing that porting. And to make that a little more user-friendly, We also expose this functionality through the unsafe wrap function. So if you have a CURA, again, a unified CURA, which is it has to be unified memory for now, you can convert that CURA to a plain Julia array using the unsafe wrap function. And then you get this object B as just a simple array object, which you can pass to every functionality in Julia that expects a simple array object. Generally, this isn't necessary, again, because we implement indexing on CURAs in a way that works from the CPU, but it's possible that you have a library which has very specific type signatures that only allow array objects, and in that case, you can use the unsafe wrap functionality to derive a CPU array object from a GPU array. This is very intentionally marked as unsafe because you are currently responsible for tying together the lifetimes of those two objects. So if, for example, you have this B object, which is a derived array, if you're using it, but at the same time you let the garbage collector collect the A object, which has the underlying memory, then you'll have issues. So for now, this is an unsafe operation. I envision that we'll fix this in the future, but this is the first step. As I mentioned, this relies on the GPU memory to be unified memory. This may be annoying to specify everywhere. So again, there is a preference now, default memory. If you set that to unified, all of your allocations will be allocated in unified memory. This, I would recommend only to do this when porting functionality. Unified memory also has a certain cost, so it's better to still switch to device memory after you've successfully ported your application and it runs entirely on the GPU. We also have the inverse operation, where if you have a CPU array object, A, you can simply convert it to a GPU object by, again, doing unsafe wrap, but now doing unsafe wrap by a CURA. This is convenient if you have a CPU application and you just want to offload a small part of it to the GPU without having to manage uploading and downloading the results. So you can just simply convert CPU memory to GPU memory. This will use heterogeneous memory management if your system supports it, which would also make this fast. HMM is only available on recent GPUs, and it depends on using the open source NVIDIA driver. So if you have both of those, then this right-hand side conversion is quick and is, again, an easy way to port parts of a CPU application to the GPU. Another noteworthy improvement is that we now track memory across streams and devices. So if you have a CURA, we actually keep track on which stream and device you allocated it and last used the memory. And this is important when you use multiple Julia tasks. Each task is associated with its own stream. You used to have to synchronize at the end of a task that produced values before using it in a different task, because otherwise you could have a race condition between the two stream objects. Because of us now keeping track on which stream you allocated and used a CURA, for example here I create a task on which I allocate a CURA, I get the object out of that task and I use it in a different task, the main task of the REPL. So those two tasks are using different streams. And as you can see with the profiler here, just simply using that array in some fill operation here, CUDA.jl detects that it's being used on a different stream, and it will automatically insert a stream synchronization operation so that you can safely pass CURAs around between Julia tasks without having to think about, do I need to synchronize this object? Is it safe to use? CUDA.jl will now manage this in the background. And the same applies to multiple devices. If you allocate a CURA on one device, you switch to another device, you start using that object, CUDA.jl will automatically detect we're now executing on a different device, so I need to reconfigure the memory allocation to expose its visibility to other devices. And behind the scenes, this will automatically use peer-to-peer communication, so NVLink or PCIe communication, if that's available on your system. In this example, device 2 is a GTX 1080, which is not compatible for peer-to-peer communication with the V100s I was using before. And CUDA.jl will let you know that it's impossible to reconfigure the system to allow this access. And in that case, you will still have to use an explicit memory copy from one device to another device, which in this case will then stage through the CPU. Finally, we also did some work on improving the GC integration, which will be valuable to many people. Specifically, we're now also freeing memory when you call into the CUDA allocator or when you're synchronizing, because those are two hotspots where at which point it's likely interesting to free up memory. And this was a great suggestion by Gabriel, and the result of which you can see on the right-hand side, where we used to go close to the line of going out of memory, and then we freed up a whole bunch of GPU memory, and over and over and over again. We now will free up fewer amounts of memory, but we'll do it much more quickly. And this is better on the Julia GC, because the GC times will be shorter, and it's also better on the CUDA allocator, because it will have to do much less work on defragmenting and compacting its memory heap. This is driven by a heuristic. So we, at every allocation and synchronization point, we have a look at the memory pressure, we have a look at how memory we freed the last time, how much time we're spending during GC operations, and then depending on that, we decide to do an additional GC call or not. So as a result of it being a heuristic, it may not be perfectly tuned for your application. And because of that, we have this environment variable that we will support for a brief period of time, allowing you to quickly enable and disable this functionality. So I would really recommend people with allocation-heavy codes to try this functionality out, disable it, enable it, observe, hopefully, improvements. If it happens, regressions, and let us know so that we can tune the heuristic to make it work better for everybody. And this is it for the highlights. There's been a whole bunch of other works. Maybe noteworthy is the fact that we shifted our support window, now supporting CUDA 11.4 to 12.5. We also support cooperative groups, which is a new way of programming GPU kernels. And of course, as has been mentioned multiple times already, enzyme support has greatly improved. There's more details about all that and all of I said in the blog posts linked below, which are the ones that we published over the course of the last year. And if you're interested in more of these, follow the blog. And every once in a while, when there's been a significant release, we post something about it on that website. There's also been a couple of oneAPI.jl releases, fewer of them, but nonetheless, we've had quite some contributors over the last year. And I guess for this crowd, the most noteworthy feature is that we now fully support Ponte Vecchio hardware, which means that oneAPI.jl works on Aurora. There's a couple of small outstanding issues with the oneMKL integration, but it only manifests in lesser used MKL calls. So generally, oneAPI.jl should work perfectly fine on Aurora. And we'd appreciate some feedback here, because I don't have access to Aurora myself. I got access to some Ponte Vecchio hardware by Intel, but we don't have the CI resources or the CI capabilities to keep track of that. So if you're using oneAPI, let us know about that. We also added support for Windows, because we know that some developers are using Windows laptops and then deploy stuff. The main way of using oneAPI.jl on Windows is through WSL. That's fully supported. It's untested in that we don't have CI resources again, but it's fully supported. Native execution we're working on. It's actually possible to compile, load, and execute kernels, but the library wrappers for oneMKL are not supported in native Windows mode. And those library wrappers are important and have been greatly extended. So last year we already supported dense BLAS. This year Alexis Montoison has been helping a lot on additional wrappers on sparse BLAS as well as LAPACK, providing all of these low-level calls as well as integrations with the high-level interfaces in Julia and Julia's libraries whenever possible. This progress has been fairly slow, because oneMKL is a C++ interface, so we have to write our own C wrappers surrounding them. So hopefully by next year we might have a C++ interoperability package allowing to accelerate these efforts. And again, there's been many more features. Brief highlights: we support a very large array now, which of course matter to people deploying on supercomputers. The launch heuristic has improved and should improve performance across the board. And we've been continuously upgrading toolchain support, currently using oneAPI base kit 2024.1.0. And again, there's been a blog post and there'll be more next year. So subscribe if you're interested. And that's about it. 20 minutes, nice in time. Thank you.
Thank you very much for the nice talk and also for keeping the time. So we do have some time for questions. Yeah.
For the dense blast support on GPUs, does it include the tensor versions of the gem call and those variations?
Should I take the mic to respond? I don't know what. The tensor operations should be used automatically by the BLAST API calls that oneMKL exposes. To my knowledge, there aren't specific entry points into oneMKL to use the tensor accelerators functionality, is there?
Well, the NVIDIA BLAST library has a separate function call for that.
It's still cuBLAST Gem and GemX, no? And it automatically uses tensors on.
Yeah, GemX,
yeah. Yeah, GemX is actually just an extended version of Gem, not necessarily enabling tensor core support or not. It's just generalizing the API. Essentially, even the normal Gem functionality should automatically make use of tensor cores depending on the precision mode that you have configured. Similarly, with oneAPI, I expect the current gem call to make use of whatever functionality it's enabled, it be tensor cores or regular warp-based multiplications.
Other questions?
Thank you for the awesome talk. One quick point, I may have Aurora access, so we should talk afterwards. I may be able to make that happen. And also thank you so much for helping me out with Dagger on oneAPI. Do you think for unified memory, in terms of writing algorithms that are generic, do you think that it is better for algorithms to generally assume that unified memory is available for Q-array inputs, or should they assume it's not, or should we be querying that? What's the right way to write algorithms for that?
They should assume it's not. However, we added it specifically to the type signature. It's a type parameter, so you can actually dispatch based on whether the array you're working with is unified or not. And CUDA.jl specifically already uses that to optimize its copy routines. If we know that we're using unified memory, we just use a plain CPU memcopy, whereas otherwise we call into the CUDA driver API.
Thank you.
Other questions? I see two over there, so maybe I can hand over the mic to you.
How will this whole unified versus separate device and GPU memory evolve from user point also in Julia if we go to architectures like Grace Hopper where this just will be much tighter? But will we still manage separately where we can, or will we just rely more on this NVIDIA Automagic?
I expect to be evolving in the direction of much more unified code. Especially so because, for example, Grace Hopper is a good example because that has gained hardware features to have much more fine-grained faulting. Currently, faulting of unified memory is implemented at the page level, so it's fairly coarse, and with some algorithms that imposes quite some overheads. But with hardware advances, both on the NVIDIA side, but also on the Apple side, where everything is unified, I expect to be moving more and more in the direction of unified memory. definitely so. We haven't explored that on the Julia side at all. So currently it's the assumption, even on, for example, the Metal backend, that we're using the memory as if it were fully separate. So there's some work left for us to be done there to explore how we best expose that and how we best preserve performance. Example of which can include, if you, for example, call functionality, we can prefetch memory, where do we automatically prefetch, do we not do that, and so on. So there's some work cut out for us.
Here. Yeah, thanks for the features and the great overview. We're currently using that through kernel abstractions. So can we all then directly use these features concerning, for example, unified memory, as long as we put the right keywords there when we allocate?
Yes, that will be possible. However, kernel abstractions currently execute only from the GPU side. So there's not that much, unless you're thinking of combining kernel abstraction kernels with, for example, CPU functionality. It would just work by switching over the allocation side to unified memory or switching the preference. So there's no compatibility work to be done on the kernel abstraction side.
Other questions there? So if you can open the mic, please.
Thank you for the fantastic talk. What's the status on kernel side launching?
On what?
Kernel launching kernels. So instead of host
dynamic
launching
dynamic parallelism. Dynamic parallelism on the NVIDIA side is supported. I don't think AMD GPU.jl, I'm not sure about, but the other backends, even though the hardware may support it, we don't implement it. But again, on the CUDA.jl side, it is supported, with the exception of H100 and GH200. The reason just being work I haven't done yet. The implementation switched. NVIDIA is using a new mechanism for dynamic parallelism, and we just haven't implemented it yet. But it is our intention to support it across the board. Currently, it does on most GPUs except the highest end ones.
Okay. Is there maybe one question we left? Doesn't look like that. So thanks again. And we're having a small break until 15:40. Thank you.